Okay. Okay, thank you for the introduction. I mean, it's a pleasure for me to be here. I mean, I'm Manuel Izquierdo from the University of the Balearic Island. I'm about to finish my PhD. So I'm very happy to have this opportunity of being able here to present some of the work I've been doing. And basically, I'm going to present this guided moment formalism, that is a new neutrino transport method, that it can be used both in neutron star mergers, core collapse supernova, or other astrophysical situations. And here the key idea is that basically it's a hybrid method that combines the base features out of the M1 and out of Monte-Carlo methods. So this is a work I have done in collaboration with Carlos Palenzuela and Fernando Avalos. And even though I don't personally don't use Einstein toolkit, I guess that this talk, it can be also interesting because maybe in the future some of you want to implement these guided moments within the Einstein toolkit, and I think it would be very interesting. But before going into what is the guided moments, I think it's better if we start by the basics, like this: what is this neutrino transport in neutron star mergers? And the situations that normally I care about or do simulations about are about a black hole and a neutron star, or two neutron stars. So we have them at their early phase. They are in this spiral. They are orbiting around each other. They end up losing energy, and they start to get closer and closer until they end merging to this coalescence. And then in late time scale, we can have this post-merger remnant. We can have this black hole surrounded by an accretion disk that it can at late times power some ultra-relativistic jets, or this neutron star also surrounded by an accretion disk. But for us, I mean, the neutrinos, they come into play in much longer time scales. And at the beginning, all the matter is very hot, very close to the remnant. But as time passes, this matter goes from being what we consider optically thick to be optically thin. So it's at this moment when this matter outflows start to expand and go out that we can observe this kilonova, and we can also study this nucleosynthesis. So this is extremely important in an astrophysical context if we want to correctly characterize what is the composition outflows of our system. And for this, it's inevitable, and unfortunately, we have to use a neutrino transport. So for this reason, I consider that it is quite relevant. And it's true that it's a caveat in current simulations because they are normally extremely expensive, and it's very difficult to simulate such long time scales. But there's always ways of being able to do it and obtain meaningful results that we can later even compare with astrophysical data. So starting by the basics, here we have a GRR MSD system in which all the contribution of the neutrinos is input as another term of the stress energy tensor. This is divided in, we divide it in three groups. We have the electron neutrinos, electron and neutrinos, and these heavy species that they are not so important. At least in this process that we consider. So for this reason, and for simplicity and computational efficiency, we gather all them in this same group. And these dynamics are mainly described by this relativistic Boltzmann equation, and also we have the MAC equations that in this case we are not going to talk at all about. So this relativistic Boltzmann equation, it would be the starting point if we want to think and say, okay, let's try to solve this neutrino transport problem. Let's try to incorporate them in our full system of equations. So this equation is a well-known equation that describes statistically the evolution of a system of particles in a 7-dimensional phase space. And the problem is that we cannot tackle it and solve it with the numerical methods that we are normally used to. And one of these main challenges is this high dimensionality. This makes it to be quite expensive. And also we have to be able to model between this optically thin and optically thin regime, and at the same time we also have to be able to model these intermediate regions. So for this reason there are several approaches. One of the most popular are these approximate methods, but the problem is that they try to simplify this let's say, to describe this physics in a simplified way, but the problem is that they don't capture the true and the nature of the solution. So for this reason, there are methods that in principle we should try to go forward to them. And there are a vast category of methods. In the past, I would say in the last decade, the most popular was this leakage scheme that instead of having evolution equations, we had a parameterization of the rate of cooling based on the optical depth, but it was well known that it has some unphysical features. Like, for example, it didn't take into account this reabsorption of neutrinos. So it was fine for the moment, but everybody knew that we needed to go forward. So for the reason, a lot of groups implementing this truncated moment formalism, mainly in this N1 version. And this is, I would say, currently the most popular by far method. And it works quite fine, but still with infinite resolution, it does not converge to the exact solution. So for this reason, there's several groups, including some talks that we have seen in this workshop. For example, the one of Matraya, that I'm familiar with his work. I mean, but other people also, they are trying to develop these full Boltzmann solvers in which they are trying to really solve directly this Boltzmann equation. Some of them, they have been well tested in the past, like for example, these Monte-Carlo algorithms, they have already been applied successfully to real astrophysical simulations. And then the one that I'm going to propose is this guided moments that basically tries to combine the best out of the N1 because it has some nice features, and of these Monte Carlo methods that they also have some nice features, but both of them have some issues as well. So we first go with this N1, and in the N1, the idea basically is to integrate the distribution function in the momentum space. So we are able to go from this 7-dimensional Boltzmann equation to a partial differential equation system in a 3+1 form. This is quite nice because the rest of the equations that we are solving, the GR equations, the MHD equations, they are in this form. So this is quite nice also in terms of implementation. But this method has a problem that is due to its own nature, and we can see it if we want to the one-dimensional case. Here we have on the left-hand side the time evolution of the zero moment. This is the energy density. And as we see in the right-hand side, we have here this derivative of the first moment. When we go to the time derivative of this first moment, we see that it appears also the derivative of the second moment. So this is problematic because this relation would go like this to infinity, and we cannot solve a system of equations like this. And for this reason, the majority of the people, what they do is they substitute this second moment that we don't know a priori for an analytical closure based on the zero and first moment they are known. And by doing this, we are able to close the evolution equations, and we are able to run simulations with it. The question is how accurate is this analytical closure? Well, we know that in the optically thick regions, I mean, when neutrinos and matter are in equilibrium, this works quite fine. It is exact, and in this part, there are absolutely no problems, and this is one of the best parts of the N1, in my opinion. But it is well known that in the thin limit, when we have these outflows very far away from the remnant, we know that normally it is not exact. It's only exact for one point source, but non-physical in the majority of the cases. So this is problematic. And basically what we do is this analytical closure is based on an interpolation between this ansat of the thin part and the ansat of the thick part. So before going to Monte Carlo, there's also one issue, but gladly this is not what I consider a real issue. I mean, it's an issue that numerically we can solve it, and is that these terms that appear here on in orange, there are terms that come from the weak interactions from the neutrinos and the matter, and the problem is that in some situations these terms can get stiff. I mean, here if we have a conservative system like this one, we here this R, it would be basically these source terms, and this 1 over epsilon, it will determine the time scale of our problem. So when this epsilon it goes to infinity, then these source terms become negligible, and we have a sweet hyperbolic system. This would be the thin limit, and we can evolve this with an explicit Runge-Kutta, and it works marvelous. But the problem is when these time scales start to get very, very, very small, then these interactions start to matter a lot, and then the nature of our equation changes, and this would be in the thin limit. And normally, what we should do is employ an implicit Runge-Kutta. So there are here several solutions. I have tried to order them from less to more clever. I mean, one of them is, of course, I mean, like if you make your time set extremely small and smaller than the time scale of your problem, even it is extremely small, then you will be able to solve it, but it would be nonsensical. I mean, like it would be extremely expensive and your simulation would run forever. Wait, sorry. Then the other idea would be to do a full implicit solver, a valid solution, but computationally expensive. Another approach, it would be to bound some implicit terms, like this would mean to try to rescale them in order to not have stiff equations. This is a cheap solution, but it's not realistic, and it goes against the nature of the community of trying to make these simulations much more accurate. I mean, like I'm presenting here a neutrino transport method, but there are also other parts, like for example, all the groups that get in charge of these neutrino interactions, that they are also really, really important. And we are all trying to go forward to more accurate simulations. And the most popular one, I would say, is these semi-implicit schemes, which are quite fine. Normally, they have two stages. One is implicit, the other is explicit. And in principle, they work fine. They are easy to implement. They are robust. But the problem is that normally they are only first order. So this could degrade the quality of our solution. So ideally, we could employ this explicit Runge-Kutta that basically is just like two different Batcher tableaus. And when the equation gets more hyperbolic, let's say, like then you only employ the explicit Batcher tableau. So you would keep this fourth order if you use the Runge-Kutta 4, or if you use the SSP3 for third order. And then the implicit part, it would come into play when this time scale starts to get very small, and in the worst case, we get at second order. So this is quite fine, and there's a lot of groups that run this N1 with the IMEX methods, and it works quite fine. And now the other part, the other main ingredient of these guided moments, it would be this Monte-Carlo, that this is a broad class of computational algorithms, and we are mainly interested in this category called direct simulation Monte-Carlo, in which the idea is to sample this distribution function by using packets. These packets, they represent a certain number of physical neutrinos, this kind of weight, you could call it, this NK. So we can characterize them completely just with the time. There are three positions, there are three momentums, this weight, and also this neutrino energy. And here in this, when we solve this Boltzmann equation, we have, I would say, two cases. One case, the good case, the best case, it would be when these collision terms are zero. So in this case, this would resemble the propagation of packets along these geodesics. And the good thing of this case is that this is completely deterministic. And this, we could get the perfect result with Monte-Carlo with only one packet. So this is wonderful. The problem comes when this collision term is non-zero. Then we have these interactions. Then we have to give some prescriptions to rule the emission, absorption, and scattering. And here the problem of being probabilistic is that, of course, the number of packets will be very important in order to get a more or less accurate solution. So this is one of the caveats of this method. So when we compare them, overall, we can see that the N1, it has a clear advantage. It is a conservative 3+1 system of equation, which is what we all dream about, let's say. We can solve it with a grid-based method that we all have implemented them in our codes. But the disadvantage is clear. It is well known, this non-physical behavior in the optically thin regions, which makes this method only approximate. Now we will assess how accurate can it be this approximation or not, even though it is very difficult to determine. And also, the majority of the people, including me, they do this gray M1, in which they only consider kind of an average energy of these neutrinos. And this makes calculations not so accurate. And it's true that there's some people that they run multi-energy M1, and it works quite fine. But the only problem is that it's in principle more computationally expensive. So this is something we will try to avoid, let's say. For the MC algorithm, we know that it converges to the exact solution. So these are good news. Also, at the same time, we can get an energy-dependent scheme, let's say, for free, in the sense that we can set these neutrino energies to each packet, and this comes with no extra cost, let's say, not like in the N1. But the disadvantage is that when these collision terms start to get very stiff in these optically thick regions, then a lot of processes take place, and they would be very expensive to run. So normally, what people do is they do this implicit Monte-Carlo. So in some way, they have to take some approximations in order to be able to run this kind of region successfully. And at the same time, when you add some approximations to your exact solution, then you will have to assess how much are you ruining this solution. And the other disadvantage is that it is well known, it's also one of the best and the worst features of this method, and is that this order of convergence scales with the power of with the number of packets to the power of -1/2, which it has a good thing that it does not depend on the dimension. So this makes these Monte Carlo methods to be suitable for high dimensional problems, much better than grid-based methods. But this slow order of convergence compared to this grid-based method makes also very difficult not only to run convergence tests, but also to make your solution more accurate. You will need much more computational power. So when we compare them in a real simulation, as far as I know, there are not so many works comparing this. There's this very nice work from François Foucault, where, as far as I know, this is the first binary neutron star merger simulation with full Monte Carlo. And here I mean, what we are seeing now, this would be this post-merger remnant. This is a three-dimensional simulation. And what they have done a cut along the y0 axis, and they have represented this electron fraction. And the first thing we see is that there's in these polar regions, there's quite a difference of this electron fraction. And this is widely believed due to this optically thin problem of the N1. Basically, some shocks are forming. This is a non-physical behavior, and more energy than it should is being accumulated in these polar regions. But the good news is that when we go to the overall composition of the ejecta, we only see a 10% relative errors, which is not quite bad. But it's true that it's very difficult to compare these two schemes, because in Monte Carlo we have the problems that we are not sure if our solution is accurate enough because of this noise. So if we don't use enough packets, we may not have a sharp solution. We also have the problem that in this simulation, it was also employed implicit Monte Carlo. So this we would need to assess how is this degrading the solution. And in the N1, basically this is run with a gray N1, so it's not having the full energy consideration. And we also have this optically thin closure. So this makes them, in my opinion, very difficult to be able to compare them faithfully, let's say. And another good news is that that this simulation was able to be run with only 10 to the 8 packets per species, which I find that for a simulation as expensive like this, it is not such a high number of packets. You can imagine that in some regions outside, in the part of the domain that you are not seeing, some parts they don't have no packets, so this makes this method quite efficient. And maybe in the core where you need to have more packets, maybe you have around 3 or 4 per cell, which I find that is a quite a small number for giving such nice result. And these simulations, they are expensive. I mean, this neutron transport is expensive, as it, in these cases, it corresponded to 50% of the cost of the total simulation. And for them, they reported that this Monte Carlo, it was same cost than N1. But of course, it depends on the implementations and the parallelization and how everything is done. So now we go with these guided moments, this idea that I'm proposing. And basically, this is a hybrid method that couples this N1 and this MC. We have seen that they have both nice and bad features. This is a work that it was inspired by some early work similar by some mathematicians, Paul de Gon, Giacomo Di Marco, and Pareschi, and also by a very nice paper from François Foucault. And here the idea is that the guided moments in the thin limit is going only to rely on this Monte Carlo solution that we know that is deterministic and it works perfectly even only with one packet. In the thick limit, we know that we will rely on this N1, that we know that it works perfectly and also is, in this case, is exact. It does not rely on probabilistics. And in the intermediate regions, these gray regions, let's say, we will combine the solution of Monte Carlo and the N1. So at the end, we end up with a closer equation for the N1. So now we also have a method that is accurate in the optically thin. Then we also have another extra feature, then this is true that this is still underdeveloped, but I think that this should be the way to do it. That is that because we are evolving this Monte Carlo, we can reconstruct this distribution function. So we could, in principle, we could compute accurate emissivities and opacities with this distribution function, accurate in the sense of energy accurate, and we could provide it and make our M1 to be also energy dependent, which would also make it much better. And even when we rely on this M1 solution, it would make it better. Also, the main problem of the Monte-Carlo, I mean, the part that is most expensive by far is these thick cells. So I'm testing some ways of trying to avoid this cost, like for example, not evolving these thick cells with Monte-Carlo, because we are not even going to care about the solution of Monte-Carlo, or running them with very few packets. And at the end, we end up having a method that converges to the exact solution in both regimes. So I don't know, I sorry I didn't mention at the beginning, but if anybody has any question, please feel free to stop me at any moment and I will be happy to answer. Okay. So when we recapitulate to this, I mean, the origin of the problem is that the present tensor of the N1 is not exact in the optically thin limit, because we said we did this interpolation and this ansatz in the thin limit is not correct. So the idea is, okay, because the Monte-Carlo gives nice information, so gives accurate information in this regime, then we modify this present tensor with information from Monte-Carlo. So what we do is we compute both present tensors, and we end up building a new pressure tensor that will rely only on the Monte-Carlo solution when we are in the thin part, and only on the N1 solution in the thick part. And in the intermediate, we will do this interpolation. So when we substitute this old present tensor for this new one that I call a PGM, we obtain what we call the GM1 solution. So in this guided moment formalism, we will have to run at the same time two methods. We will have to run the N1 and we will have to run the Monte-Carlo. So in this case, for the moment, we're running them separately. And now that we have this nice pressure tensor from Monte-Carlo, we give it this information to this N1. So what we call this GM1, it would be a normal N1 with a modified pressure tensor, which makes it to be exact. This is what we call this GM1. It would be what we call the best solution, or the true solution, or the exact solution. There will also be an auxiliary solution that it will be the one from Monte-Carlo. But this solution is only for purposes of being able to provide this information for the N1, but it will not be employed in other calculations. So this way of interpolating, it was deeply based on the original idea of having also this interpolation in the N1 of combining these thin and thick limits. And this transition function, I feel that is probably the most delicate and at the same time the most important part of these guided moments, because depending on how you choose it, you will have one behavior or other. But for the moment, you only have to care that this numerically is a combination that have been able to work quite fine, and is to take less N1 and more MC. And this for the moment has proved to be the best way, let's say, but this could be further and easily improved. So this is also a matter of still under development. But the important part, and the part that it was missing on this work from Francois, that he was trying to do the same as until I have described it, let's say, it was that when you have this GM1 solution, you have this Monte-Carlo auxiliary solution, you are feeding this pressure tensor. The problem is that eventually these two schemes could start to lead to different solutions. So they will end up diverging, and this would make the simulations unstable. And this is what Francois observed. So for avoiding this, what we need is a fully coupled system. So we also need to provide information from the N1 to the MC. So we are completely sure that both of them run in the same direction, they run to the same solution. So for doing this, for connecting this MC and this N1, you have to remember that this Monte-Carlo is a particle inset method. So we have this position, these momentums, and for the other side, we have this N1 that is a grid-based method where we are evolving directly these moments. So for connecting them, basically what we have to build is we have to build this covector, which is basically the collection of this zero moment and this first moment. So what we thought at the beginning, it was, okay, after giving this information from Monte-Carlo to this N1, now we have a correct pressure tensor, everything should work smoothly. Now we can restart this Monte-Carlo and we can reset the moments of Monte-Carlo to be the same one as the M1. When we did it like this, we were modifying too much the behavior of Monte-Carlo, and at the end, we end up having pure M1, which means that we didn't solve this optically thin problem because we were not letting this Monte-Carlo solution to run freely. So instead, what we do is we do the same idea as before, and we do the same idea as before, and what we do is we modify these moments of Monte-Carlo, but we modify them in a way that when they are in a thin cell, we don't touch them because we know that the Monte Carlo solution would be more accurate. In the case of the N1, when they are thick, we know that the moments from the N1 will be better. And in the intermediate, we do also this interpolation. So what we do is we substitute these lowest moments of Monte Carlo for these new moments that I call GM. And this is this GMC solution, that this will be auxiliary but necessary in order to run the system. So this transformation, I mean, because as you can see here, we have here these new lowest moments that we want to set to this Monte Carlo, but remember that we have particles. I mean, we don't have moments in Monte Carlo. So how can we do this? We can do it by transforming these momentums of Monte Carlo packets in order to point in the right direction that makes them to also match the lowest moments of this GM solution, let's say. So this is done by this Lorentz puzzling, and these are some transformation matrix that you have to compute at every cell and at every substep. And basically what they do is they transform a given initial 4 vector to a final one. They have all the properties that we wanted. They preserve their norm and they preserve their time like nature. So basically, we know that these new moments, they will be exactly the same as Monte Carlo in a thin cell. They will be exactly the same as M1 in a thick, and the intermediate, they will point in an, let's say, like the proportional direction. So just to recapitulate before going to the numerical results, we have these. We have two solutions. We have the best solution, that is this GM1 solution, that basically is a normal M1, just that it has a modified pressure tensor, this new pressure tensor, that in the thin limit it would be exactly the same as the Monte Carlo one, in the thick exactly the same as the M1, and in the middle an interpolation. We also have this auxiliary solution, this GMC solution, that it would be a normal Monte Carlo, just that at every substep we reset some moments. In the case that it is a thin cell, we don't touch them. In the case that it is a thick cell, we set the ones of the N1. And in the intermediate, we also do this interpolation. So now we go with this numerical test. And this first one is this very famous double beam test, that this is a two-dimensional test in which basically here what we are portraying is this energy density, this zero moment. And here you can imagine this as a beam of neutrinos that are being injected from the boundaries. And here in the M1, what happens is that these neutrinos, they intersect, they collide, there's a shock form, and they end up propagating in the average direction. This is this non-physical behavior because the problem is that the closure that we are putting does not retain the information from the direction of each beam. So this makes this N1 to be problematic at this point, and also neutrinos should not interact between them. In the case of Monte Carlo, this can be run smoothly and they cross without any trouble. In the case of this GMC solution, as you can see, it's exactly the same as this MC solution, because in this case, this is a purely optically thin test. So this means that the GMC is not being modified at all because it's only thin cells. And here, this our let's say best solution is this GM1 solution. That, as we can see, we are able to modify this nature of the N1, and here now we are able to see that these beams they cross successfully. The only problem, let's say, of this test is that when I first ran it, I ran it with 100 packets per cell, which is a huge number and nonsensical because, like in real astrophysical simulations, like the one I saw before from Francois, like he employed around 3 to 4 packets in the most dense cells. So I try to run it with less packets. And for doing this, I also try to explore different transition functions. This was just I'm still like working on it, and there's still not finished work. And here you don't even need to really care about exactly which numbers are here. You can just imagine this as a transition function in which what we are deciding is at which point we go from taking M1, this would be M1, or taking more Monte Carlo. So depending on the situation, we can test different transition functions, that it will change also the nature of how we are doing this interpolation, and we observe different results. So we observe that in the case that in this case, this would be this GM1 solution. It's exactly the same test as before. And what we see is that in the case that we take much more Monte Carlo and less M1, we see that we are able to run successfully this problem with only 1 packet per cell. So we know that in this case, if the cell is very thin, this GM1, it will work only with 1 packet per cell, which is an extremely nice result. We see that as we move this transition point, I mean, like this chi0, I mean, like when it starts to get bigger, it means that we are taking more M1 than before. So as we go increasing the number, we see that the solution starts to degrade a little bit. And then when we start to increase the number of packets, here 5 packets, we see that now this one, it runs perfectly. This one is a little bit better. And with 20 packets, we see that this one is perfect. And this one, it starts to get much better. Here we can also see what I mentioned, that if you want to see a great improvement of the solution due to this low order of convergence, you will have to employ many more packets. And then the other simulation that I'm going to, the other result that I want to present is this radiation and absorbing torus test. This is basically, this is a three-dimensional simulation. This would be a very simplified case of what could it be a real accretion disk in a real astrophysical scenario. And in this case, we are also this three-dimensional simulation. We have done a cut along the y0 axis. We are also representing this energy density. And when we go to the M1 solution, we see that the interior, that this would be very thick, like very optically thick. We see that the solution is perfect. It is super sharp and well defined. And the only problem it comes in these polar regions, that basically you can imagine here there's a lot of beams crossing, like this double beam test, but in this case it would be in three dimensions. So you can see that some energy is getting deposited in these polar regions, and this behavior is non-physical, and it could change the result of our simulations. When we go to the case of Monte Carlo, we see that in this interior, these thick cells, this is the part that is probabilistic. So if we want to get a sharp solution, as sharp as the one from M1, we should employ many more packets. We see that here is still a little bit noisy, and we see that outside it's also a little bit noisy, but the good thing is that we don't have this bad behavior of these bumps. So this is the exact solution. And our best solution, it would be this GM1, that as we can see, the nice feature of this guided moments method is that the interior, we have been able to keep it perfectly. I mean, like it would be basically a copy paste, so it looks perfect. And at the same time, we have been able to remove this unphysical behavior on these polar regions. So this would be by far the most accurate solution, at least comparing between these two methods. When we go to this GMC case, we see that the exterior is exactly the same as Monte Carlo, because this part we are not modifying, but because we are doing this matching of these lowest moments, we are also doing this kind of copy-paste from the same one. So in this case, this simulation is run with a parameter that is called a trigger, and at least in my implementation, basically is what allows me to control the computational cost. And this decides exactly how many packets do I want to emit per cell and per time step for a certain value of the emissivity. So in this case, this means that at every time step, we are emitting in this interior of this accretion disk 4 packets per cell, which in this case, it would be more or less close to these real astrophysical simulations. But also, I tried with only 1 packet per cell to see what happened. And when we do it, we see that the N1 is exactly the same because we didn't change the spatial resolution, so it's exactly the same. When we have only one packet, we have this Monte-Carlo, it starts to get extremely noisy. The solution in the interior looks horrible. But when we go to this GM1 solution, then we see that the interior, it looks quite sharp and defined as the one as M1. And the exterior, it looks quite decent in my opinion. I mean, like I can put it again and compare it. I mean, like it does not look as sharp as these as the case with 4 packets per cell, but still, in my opinion, it looks quite decent and is still better than what we have for the moment. As you can see, this MC. For the GMC, we can see that we have also sharp interior, but it's extremely noisy outside. So just concluding, I think like the majority of the people could agree that this N1 and MC, they give reasonable results. I mean, we can extract information from them, but they have limitation, and at some point we need to go forward and make our simulations more accurate. So here I'm trying to claim and convince you that this GM captures the best out of this N1 and this MC, as we are able to provide this exact closure of this N1. At the same time, because we have this distribution function information, we are able also to have these energy-dependent emissivities and opacities. And from this double beam test, we have seen that we need a low number of packets in the limits, as in the case of the N1, it doesn't matter the number of packets, and in the case in the thin limit, it does also not matter because this part is deterministic. The question still open is how many do we need for these intermediate regions, and this will only be, let's say, like check, and we will know exactly when we are able to run real astrophysical simulations. And for this reason, I mean, all the results that I have presented, this has been done in a test code that I have developed, but now I'm currently implementing them in the code that I normally use, this MH duet code, and it comes here with parallelization, and now we were transitioned to this IMRX, so we can run it with CPUs. We will get a paper very soon out of all the details on the implementation. And for the moment, this is what I'm trying to do. And fortunately, when I'm able to finish this implementation, we will be able to see and finish, let's say, deciding this transition function, and we will see how does it work and how does it compare with this N1 and this Monte-Carlo in a real astrophysical simulation. So this is all. Thank you, and if everybody has any question, I will be very happy to answer.
Leeway, I see you've raised your hand. Would you like to ask a question? Go ahead.
Yes, great talk. So for the guided M1 case, so I'm just curious about the order of number of packets compared to pure MC.
Oh, pues in this case, I mean, like for the moment, for what I have seen, I mean, like you can check it here. The good thing is that because the place where you need more packets in Monte-Carlo is these thick cells, and we are avoiding to use this solution in this case. I think that in the future, I mean, my idea, my hope, and what I'm trying to develop is basically to be able to run it with just very few packets. This means that the cost of the Monte-Carlo, it should be much smaller than the current cost of a single Monte-Carlo method, because we don't need the solution in this kind of cells. So this is like the part that is like I'm trying to figure now. But in principle, at least my dream is to be able to run them with very few packets. And I'm also trying to develop a new, let's say, a new version of these guided moments. It would be a local guided moments. That it would be that instead of evolving these packets over the whole domain, we would evolve them just locally at every cell. So this would be just like a kind of an extra routine attached to this N1. So by doing this, we would be able to run these cells, this local Monte-Carlo with a lot of number of packets, because basically we just evolve them and we would just throw them away, let's say. I mean, we would not have to keep them in memory, and this would make it extremely computational efficiency. And by doing this, I think that we would be able also, for example, to have a great estimation of this distribution function.
I see, thanks. So do you have estimation about a rough number of how many packets will be needed for guided M1?
Pues I'm not sure. I'm not sure exactly about the estimation, but I think that if current simulation have been able to do it with 4 packets per cell, I guess that it should have to be smaller. So I guess that at most 1 or 2 packets. It depends. I mean, like in the free streaming regions, with 1 packet you get the right solution. So maybe with 1 packet per cell it could be fine.
Okay.
Or maybe 2. I don't know. But I hope it does not have to be more.
All right, thank you. Jonah has his hand raised. Jonah, would you like to ask your question?
Yeah, thanks for the nice talk. So I wanted to ask, you hinted about the spectral information that you want to include, but you didn't, maybe I missed it. What are you currently doing? So the moment method sounds like it's gray. Are the particles also gray? How are you picking their energies?
No, in this case, I mean, this is still like underdeveloped, because for the moment I'm only running simulations in which I have fixed emissivities and opacities. So in this case, energy is not it does not come into play. But in the future, the idea is you will run a gray M1, but instead of using these integrated, let's say, these gray opacities and emissivities, if you include in the integrals this distribution function, you could get, let's say, like the integrated, but in this case, energy dependent emissivity and opacity. So this would be your source term for this GM1. And because they come into play mainly in these thick regions, so they will come into play in your GM1 solution. So this is the idea, but for the moment, I have not been able to test it, let's say.
I'm not sure I totally understand. Are you going to move the M1 method to multi-group then? And leave the particles gray, or are you going to do multi-groups on the particles, or are you going to do continuous energy on the particles, or some combination?
I think the idea would be to do energy-dependent particles, a gray M1, but with accurate energy-dependent emissivities and opacities.
Okay, I
By
see.
computing them with this distribution function. I mean, this is the idea, but it's true that it also seems that in current simulations, it's also difficult to have a good estimation of the distribution function. So this could ruin a little bit. Like, you need to have a good distribution function, a right one at least, like, in order to work this what I have said.
Okay, I see. Yeah, that's a nice idea. I think you'll need more than 1 or 2 particles per cell to do that, though.
Yes. For this reason is the reason why, more than focusing on this, is I'm trying to do these local guided moments, because if this works, then I think there would be no problem with the distribution function, because you could easily employ, let's say, 100 packets per cell and have a super sub Monte-Carlo solution, let's say. But this is still far work to do, let's say.
Okay. Cool. Thanks.
Lucas,
So,
if you speak up, it'll catch you.
okay, thanks for the talk. Could you try and provide some sort of like mental model or physical intuition to why that neutrino interaction curve that you showed in the beginning turns stiff, right? Like I understand it sort of in a mathematical sense why that can happen, but if you could like try to link that to some, what in the physics is happening that makes that term turn stiff, right? Where is there a time scale change or something like that?
Yes, I mean, it's in principle that the time scale changes. So, I mean, the nature of your problem, it changes. But I mean, like, in principle, I would say that it's more a numerical problem, let's say. Like, if you are able, I mean, like because the time scale of your problem is changing and is reducing a lot, you would have to change the time step that you are taking in your simulation, because if not, you are not able to capture all the information.
Thanks.
Great. Yeah, Jay, you have a question? Would you like to unmute and ask it?
Hi, thank you. Thanks, Manuel, for the great talk. Just a couple of questions. One, I was wondering, following up on Liwei's question about what's the computational cost when you consider just one packet per cell for the GM1 versus a pure M1? And also, the next question is, have you done any scaling tests, both either on CPUs and maybe also on GPUs with Amrex? Yeah, so it'd be great to know.
No, for the moment, the scaling test, I have not been able, I mean, like the M1, that is the only thing I have been able to try. It runs much better with GPUs, but still the Monte-Carlo module is not finished, so I have not been able to still like completely couple and combine this M1 and this Monte-Carlo. And regarding this computational cost, I think like the key part is, I mean, like the reason why still I have not done all these kind of assessments is because the problem I feel that is this cost of the Monte Carlo in these optically fixes. So if you are able to avoid it, then I think at least I mean like the M1 is always going to be exactly the same as everybody that does a gray M1 is not going to be more and not going to be less. And the Monte Carlo, I think the key is the thick packets. I mean, like if we are able to find a nice solution in which we don't have to evolve these cells, or we can evolve them with only one packet and not ruining the rest of the solution, then it will be very, very small cost. I mean, like in the worst case, the worst case, it would be you implement a Monte Carlo method exactly as the same one, for example, like the one from Francois, you do this implicit Monte Carlo, you do it as it is now the moment, as it is now these guided moments, and it should work, but you would get a method double expensive, let's say, like you would get the cost of MC and the cost of M1 if you do it directly and you don't change anything. So that's the reason why we want to avoid this, and it's worth it for us to try to make it better, because making the simulation double expensive is not something that that we are looking forward. Even with GPUs, even with GPUs, would not be that great. But I would say double cost, it would be worst case, and best case, it would be M1 plus very few, let's say.
Great, thank you so much.
We have another question here.
Hey there, very nice talk. I have a question about boundary conditions. So do you basically evolve the M1 everywhere in the domain and just discard it, or replace it with the Monte Carlo or the guided moments? Or do you have some boundary conditions where, I mean, you need to, it's the fields are going to be defined everywhere in the domain, right? You're going to have some boundary conditions where you blend it together. How do you do that?
Well, I mean, like at least in all the simulations that I'm considering, I mean, this is not very problematic, because all the boundary conditions that I'm considering, they are radiative. And in this case, I mean, like when you have this, I mean, like the real, let's say, like this neutron star merger simulation, I mean, you have such a huge domain that in principle, at the end of the grid, I mean, like nothing is reaching. And when you have this Monte Carlo, you are going to be sure that absolutely no packets will be there. So I think like it would be the same. I mean, like you don't need to do anything special in comparison with, for example, the MHD equations. Let's say, I mean, you just impose these radiative boundary conditions because you don't want any bad effect bouncing in the grid and coming back. You just want it to slowly dissipate it. But it's not something I would say particularly challenging, and not something that would really be problematic for the guided moments or for the M1 of, well, I mean, Monte Carlo, I would say, is the most efficient in that sense by the nature of the method. But the M1, it would be the same as other kind of equations, and the same as the GM, yes.
Thank you.
Yeah, Johnny has a question. Here you go.
Thank you. So I have a question about when you were mentioning when you're evolving M1, there is a stiff term in the source term, and that's why you choose to use this explicit method. So I'm wondering why would using the guided moment remove this, I guess.
No. I'm sorry if this was the impression that it gave, but no. I mean, unfortunately, this is let's say like a something that you have always when you evolve the M1 and when you evolve the guided moments, as you are also evolving the M1, you also have it. So we also use this. The good thing is that we also use this implicit explicit Runge-Kutta, and the good thing is that the explicit part, the explicit table, we are able to employ it for all of the rest of our equations. I mean, like Einstein equations are evolved with this Runge-Kutta 4, the MHD, the fluid, everything is being evolved with this Runge-Kutta 4. So this makes all, let's say, like you solve everything at the same sub-step, let's say. But yeah, this is something that, like, even if you use these guided moments, you have to care about. I mean, like in terms of implementation, if you are just testing, when you try a semi-implicit scheme, is the easiest way to implement it, let's say. But if you want to make your code a little bit higher order, depends also on the method, on the other order of the methods of the other part of the equation that you are solving. But yes, I mean, in principle, with a semi-implicit scheme, it should work fine.
I see. So in terms of time step, like GM1 or GMC would have the same width if you evolve it with MC or M1.
Exactly. Yes, exactly. I mean, and the good thing is that in this case, I mean, like we did a paper on this basically because we were trying to find one IMEX method that basically coupled with this Runge-Kutta 4, because this Runge-Kutta 4 is nearly strong stability preserving, but the good thing is that it has a very high CFL. I mean, in one dimension, it has a CFL of 2, and it has 4 stages. And the good thing is that when we couple with this implicit table that is second order, we don't need to reduce at all the CFL. So we are able to run, in this case, even though there are some stiff turns, we are able to run it with the same effective CFL as if we were not evolving these neutrinos. I mean, it is true that because you have some implicit calculations involved, it will make the calculation more expensive than it would be only explicit. But in terms of CFL, we are able to evolve it all. I mean, like all the simulations in 3D, we run them with a 0.4 CFL in 3 dimensions. And like this, for us, it works perfectly. And we are in the safe side. I mean, we could push it a little bit further.
Thank you.
Right. Let's see. Any other? All right. Are there any other questions in the room? Yeah. So I had a question for you. I really like this this approach. A couple questions. First, could you comment briefly on to what degree the algorithms you presented have been open sourced?
Okay. Yeah, this is a nice question because I mean, basically, there are 2 codes. I mean, there's the main code that is this MH2 that I was saying that I'm now trying to implement it, and this IMRX implementation. This code is completely open source. I mean, like you can check here in this web page, and you can download it. I think right now it is not still the last version, but we are waiting for finishing cleaning all the bugs of IMRX, and as soon as we have it, we will release it. So this is full open source, and it has always been. The other part is that these guided moments, like the test that I have shown, this has been done by a code that I have developed. This code for the moment is not open source, but just because I have not had time to clean it and purify it a little bit. But my plan is when I have more time, I will try to put it. I will have to put it in GitHub as an open repository, and I think it will not be useful in the sense that the people will couple it through their simulations, but it would be useful in the sense that for development, for testing things, and for checking what is the implementation and then translating it to your code, this can be useful. I mean, and this code is written in Julia, and it runs with GPUs and is parallelized.
Interesting. So it's running in Julia. Interesting.
Yes.
Oh, okay.
But
Wow.
the main code is it's C++.
Yeah. Let's see. My second question, hopefully a relatively quick one. So in these code tests, generally we're looking at or analyzing objects in a fixed frame. I am curious, given the potential for challenges in a boosted frame, I'm curious if it would be helpful to, I mean, there are a couple of ways of doing this. One is you just Lorentz boost everything from a normally fixed frame code test. Another is just set the shift vector in one Cartesian direction to a constant, and things will just naturally move along the grid. Have you given any thought to this, or do you have code tests where we're not in a fixed frame?
Yes, I performed one that it was basically to mimic the same one as this boosted sphere that it appears in the paper from Francois, and with the guided moments. Unfortunately, I don't have it here in these slides, but the result that I observed it was that it was better than the result that Francois obtained. But yeah, I have to say I did not. I mean, like it looked fine, but I have to say that apart from this, I did not give it much a try, because I mean the implementation that I did in this Julia code is only, let's say, special relativistic. But for sure, when we do when I finish the implementation in this MH2 code, for sure this will be tested all possible scenarios, and this would be important. Yes, of course, yes.
Great, thank you. Any other questions? All right, well, let's thank our speaker again.
Thank you.